Hey, welcome to the derivative and tangent line problem. My name's Tuesday J. Johnson. I'm a lecturer at the University of Texas El Paso and an assistant professor at Doña Ana Community College. This lecture is for Math 1411 Calculus at UTEP. Chapter 2, Differentiation, comes from Larson's 11th edition calculus text. Section 2.1, the derivative and tangent line problem. So what is a tangent line? A tangent line is, first of all, it's a line, so it's linear, all right? It's a straight line that touches the graph of a function in only one place. Now, over here in the second graph, this red line is also a tangent line, even though it touches the graph in two places, because a tangent line, it touches the graph in only one place near where we're talking about. So near this particular point, x comma f of x, the tangent line only touches once. Even though it might touch later, that's all right. Why do we care about tangent lines? Down here in the bottom, we have this nice blue curve, and we have the tangent line and a little pull-out menu of it. And see how near the point, the blue curve is approximated by the straight line. So in this area, they're essentially the same thing. We know a lot about lines. We can make predictions with lines. We can do a lot of things with lines. We understand lines a lot more than we understand curves. And so we'll use this tangent line to tell us a little bit about what's going on at a particular location. Tangent lines start with the difference quotient. And the difference quotient is from pre-calculus. It's a generalized form of the slope formula. So f of x plus h minus f of x all over h, difference, right? Subtraction, quotient, because we have division. This difference quotient forms the basis for differential calculus. It's essentially half of calculus, the derivative. Let's take a look. Starting with a definition, the tangent line with slope m. If f is a function that's defined on an open interval containing c, and if the limit as delta x approaches 0, so delta y over delta x, change in y over change in x, this is just a slope formula. If that is equal to the limit as h approaches 0 of f of c plus h minus f of c all over h, which we're going to call m, if these limits exist, then the line passing through the point c comma f of c with slope m, it's the tangent line to the graph at the point. Specifically at a point. A fact is, the slope of the tangent line is sometimes called the slope of the graph at the point, or the slope of the graph, depending on how loose we want to be with terminology. So let's take a look at a basic example. Find the slope of the tangent line to the graph of the function at the given point. Now I'm going to do a couple of things here that will make no sense later on, but just go with it. Our first example, f of x equals 3/2 x plus 1. Our point is negative 2, negative 2. Now remember, to find the slope of the tangent line, we're going to look at the difference quotient, and the difference quotient in steps with a particular c value, negative 2. First I find f of negative 2 plus h. So everywhere there was an x, I replace it by negative 2 plus h. 3/2 times negative 2 plus h plus 1. The 2's cancel. I'll end up with negative 3. Plus 3/2 h plus 1. And the positive 1 and the negative 3 combine to give me a negative 2 plus 3/2 h. This is f of c plus h. This is f of c. F of negative 2. Well, if I put negative 2 in for x, 3/2 times negative 2 is a negative 3 plus 1 makes negative 2. Now, this is one of those ridiculous things I just did. I know that the y value when x is negative 2 is negative 2 because it told me right here. Sometimes we need to remember to work smart and not hard. I could have just known the f of negative 2 equals negative 2 by the given point, but I did the work. It's nice to know that they match up. Continuing this example, so we have f of negative 2 plus h simplified minus f of negative 2 all over h inside of the limit as h approaches 0. The negative 2 minus negative 2, they cancel out. I'll end up with 3/2 h over h, the limit as h approaches 0 of this quotient. But the h's cancel, and limit as h approaches 0 of 3/2. Remember, 3/2 doesn't care what h is doing. 3 halves is just hanging out being 3 halves, whether h goes to 0, h goes to 4, or h goes to a different school entirely from what you do. 3 halves is just 3 halves. This tells us the slope of the tangent line to the graph of our function at a c value of -2 is 3 halves. Now here's the other part of the example I just did. This is a linear function. We know the slope of any tangent line is the line itself. The slope of a linear function 3 halves will be the slope of the tangent line because the line itself is its own tangent line. So the slope of any linear function is also going to be the slope of the tangent line. So let's do a non-basic example. Taking g of x to be 6 minus x squared, and the point 1, 5, this top line is given to us. Since c equals 1, I'm going to find g of 1 plus h. So that's 6 minus 1 plus h all squared. 1 plus h all squared, don't forget to FOIL. Don't just square the 1 and square the h. Make sure you write it out. 6 minus, in parentheses, 1 plus 2h plus h squared. Distribute your negative to the 3 terms in the parentheses and combine like terms to get 5 minus 2h minus h squared. Now we're going to work smart instead of hard. I know that g of 1 will equal 5, so I just jump straight into my difference quotient. The slope of the tangent line is given by the limit as h approaches 0 of 5 minus 2h minus h squared, right, g of 1 plus h, minus 5, g of 1, all over h. 5 minus 5 cancels out. The limit as h approaches 0 of -2h minus h squared over h. We can see that every single term in this quotient has an h in it. I encourage you to write it in factored form so you don't lose track of your powers. If you factor out the h from the numerator, you'll be left with a -2 minus h. And that h that you factored out will cancel with the h from the denominator. And so we're looking at the limit as h approaches 0 of -2 minus h. When h goes to 0, this will be -2 minus 0. I sometimes cancel this out and say it goes to 0. -2 is the slope of our tangent line. Couple of other notes. Notice, until I actually substitute and let h go to 0, I have to continue writing limit. And I can't just write lim h approaches and then equals. It's the limit of what? I have to have an expression in here, a function that's going on that I'm taking the limit of. So be careful with notation. Looking at a graph, the graph of g of x equals 6 minus x squared. At the point 1, 5, right, I drew the equation of the tangent line. The slope of this tangent line is -2, as we just found. You can check it from the graph. Slope is down 2 over 1. Down 2 over 1, down 2 over 1, and I have exactly the right slope of the tangent line for this example. Our third example, r of t equals t squared plus 3 at the point -2, 7. Using a c value of -2, we can find that r of -2 plus h, right? r of -2 plus h, our c plus h, is 7 minus 4h plus h squared. Inputting -2 plus h in place of the t, squaring that, making sure to FOIL, and then adding 3. If you need to pause, make sure you write it out and see where that came from. Resuming, r of -2, I know that's 7, right? Work smart, not hard. Using this in the difference quotient, the limit as h approaches 0 of 7 minus 4h plus h squared minus 7 all over h. The 7's cancel. That's the limit as h approaches 0 of -4h plus h squared all over h. If we factor out our h, we'll be left with a -4 plus h in the numerator. The h that we factored out cancels with the 1 in the denominator. And as h approaches 0, we'll end up with -4 plus 0, which is -4. So the slope of the tangent line to the graph of r of t equals t squared plus 3 at the point -2, 7 is -4. Now, the derivative at a point is nice, but as it turns out, the derivative is also a function. So the derivative of f at x, in general, not a specific point, but in general x, is given by f prime, this little apostrophe looking thing, we call that a prime. F prime of x equals the limit as h approaches 0 of our difference quotient. In general now, instead of at a specific value c. This is provided the limit exists, of course. And f prime is a function of x, as I originally stated. A couple of different notations. F prime of x, the one I've used here, that's the same as dy dx, y prime, d dx of f of x. Or when you get into later calculus 3 and differential equations, sometimes we'll use the capital D notation. The subscript or the denominator will tell you your variable, and in parentheses, or the variable in the numerator along with the d operator, is what we're finding the derivative of. So f prime of x tells us find the derivative, but d dx says find the derivative using x as your variable for the function f of x. Similarly for y. If we want to find the derivative by the limit process, here are the steps that we're going to use. Again, right, basic example, we know the slope's going to be 3, the derivative must be 3, the derivative is the slope of the tangent line. Let's take a look. Step 1, I'm going to find f of x plus h. So everywhere there was an x, I'm going to replace it by x plus h. Distribute 3x plus 3h plus 2. Step 2, I'm going to write down f of x. Step 3, I'm going to find the difference. F of x plus h minus f of x is 3x plus 3h plus 2 minus the original function. And when I subtract that original function, notice I'll have 3x minus 3x. I'll have 2 minus 2. And the only thing I'm left with is a 3h. At this step, it's the end of step 3, after you simplify, every single term should have an h remaining in it. And we'll see why in a couple more examples. So I found the difference. Now let's find the quotient using the limit. Step 4, the limit as h approaches 0 of our difference, 3h, all over h. H is cancelled. The limit as h approaches 0 of 3 is just 3. So remember, the derivative is equal to this limit. So the derivative is 3. The slope of the tangent line, derivative, slope of the tangent line, is 3 for every point on this particular graph. Now let's take a non-standard example. If I have g of x is 2 minus x squared, first step I find g of x plus h equals 2 minus x plus h all squared. Don't forget to multiply it out, FOIL it out, don't just square the x and square the h, you'll miss some good stuff in the middle. Distribute your minus sign. Alright, so that's g of x plus h. G of x plus h. When I subtract g of x from this function, I could do it in a couple different ways. Maybe I would just go right underneath here and I would subtract 2 and subtract x squared. And from here we can see how the 2 minus 2 cancels out, the negative x squared minus negative x squared cancels out, and all I'm left with are the terms that have h, minus 2xh minus h squared. So I have my difference. Let's check out this quotient. The derivative of g is the limit as h approaches 0 of my difference all over h. Notice there's an h in each and every term, so factor that out and cancel. We'll have a limit as h approaches 0 of negative 2x minus h, and as h goes to 0, my slope will be a negative 2x. How does this help me? Well, if I want to know the derivative at 1, I can now evaluate it here. What's the slope of the tangent line when x equals 3? I can evaluate the derivative and find the exact slope at that particular point, rather than doing the process over and over again for many different values. Alright, f of x is 4 over the square root of x. First, we're going to find f of x plus h. No problem. Replace x by x plus h. Anytime it seems easy at the start, there's going to be some work to do. So, f of x plus h minus f of x is f of x plus h, 4 over the square root of x plus h, minus 4 over the square root of x. There's nothing that cancels here. It's going to require some algebra. Taking our difference, 4 over the square root of x plus h minus 4 over the square root of x, I want to find a common denominator, so I'm going to multiply this first rational expression by the square root of x over the square root of x. I'm going to multiply the second rational function by the square root of x plus h over the square root of x plus h. That way they have the same denominator, and I'm not even going to multiply it, I'm just going to write them next to each other. But I'm going to rewrite this first expression as 4 square root of x over the common denominator, minus 4 square root of x plus h all over the common denominator, and then write it as a single fraction. 4 square root of x minus 4 square root of x plus h all over the common denominator of the square root of x plus h times the square root of x. That whole thing goes in our, that's our difference, right? Goes in our difference quotient. So f prime of x is the limit as h approaches 0 of the nasty stuff from the last slide, all divided by h. But when h is 0, my numerator is 0, my denominator in the numerator is x, so 0 over x divided by 0, that's 0 over 0. Unfortunately, a common denominator wasn't enough in order to be able to evaluate the limit, right? This is an indeterminate form. Anytime you get 0 over 0, you have to do something else. More algebra. So, I have my numerator from the difference quotient, 4 square root of x minus 4 square root of x plus h, all over square root of x plus h times the square root of x. To rationalize the numerator, I'm going to change the sign in the middle, right? It's a binomial, 2 terms. Change the sign in the middle. When I multiply in the numerator, 4 times 4 is 16. The square root of x times the square root of x is x. Notice that the outside and the inside, when I multiply using FOIL, will be a positive 16 couple of radicals and a negative 16 couple of radicals. They cancel out. So I'll have the negative times a positive is negative. 4 times 4 is 16. Square root of x plus h times the square root of x plus h is x plus h. And I put it in parentheses because the 4's were multiplying by the entire radical. So when we multiply, we have to make sure our 16's are multiplied by the entire radicand, the thing under the radical. Notice again, I chose the lazy method, and I just wrote the denominator in completely factored form. 16x in the numerator minus 16x cancels out. A negative 16h is all that remains. How does this help us? Let's see. A negative 16h over my ugly denominator, all divided by h. Oh, look at that. The h's cancel. So I'll have negative 16 over ugly denominator. That's what I'm going to call it officially. If h goes to 0, I'm going to replace every single h with a 0. So that's the square root of x times the square root of x. 4 square root of x plus a 4 square root of x. So I'll have a negative 16 in the numerator and x, and 8 square roots of x in the denominator. Negative 16 over 8 simplifies to negative 2. X square root of x. That is an ugly derivative. But where was the calculus? Calculus was only in this step, substituting the h. The rest of it's algebra. It doesn't make it easy. It just makes it algebra. So, some examples. Find the equation of the tangent line to the graph of f at the given point. Equation of the tangent line. It's a line. The equation of a line has form y equals mx plus b. We call this the slope-intercept form. So we need to find our slope, derivative, and our y-intercept. The best way to do this in calculus is to remember that slope is the derivative, and then use the point-slope form of the equation of a line. Our strategy is to find f prime of c, and then use the point-slope form with our given x value and our given y value to find the equation of the tangent line. So if we're given f of x equals x squared plus 3x plus 4 at a point negative 2, 2, first we find the derivative. Finding the derivative using the limit definition, that's f of x plus h equals x plus h squared plus 3 times x plus h plus 4. FOIL out your x plus h all squared to get x squared plus 2xh plus h squared. Distribute your 3 to get 3x plus 3h. And don't forget your plus 4. When we subtract the original function, right, we subtract x squared, we subtract 3x, we subtract 4. The only things that remain are the ones that have h in the term. And not just finding the difference, I'm going to go ahead and find the quotient as well. The difference that we just found, divide everything by h. 2xh divided by h is 2x. H squared divided by h is h. And 3h divided by h is 3. Now, we know the derivative is the limit as h approaches 0 of our difference quotient. When h goes to 0, we'll have 2x plus 3 as an equation of our derivative. Sometimes it's good to go back to the instructions. Find an equation of the tangent line. Equation of a line. Alright, all I did was find an equation for the slope. So my particular derivative at an x value of -2, that's 2 times -2 plus 3. That's -4 plus 3, which is -1. So finally I have my slope, I have my point, I have everything I need in order to find the equation of a tangent line. The f prime of -2 equals -1, a c value of -2, and an f of c value of +2. We have y minus 2 equals slope derivative -1 times parentheses x minus a -2. In my next step, I just change the subtracted negative to adding. Distribute the -1, so I have -x and a -2. Add 2 to both sides, y plus 2, y minus 2, and I add 2, I get y. A -x minus 2, add 2 to that side as well, and I'll get y equals -x. I gotta tell you, that was a lot of work to get an equation of y equals -x for the equation of the tangent line to the graph of f at that particular point. So let's do it again. Find an equation of the tangent line to the graph of f at the given point. F of x equals the square root of x minus 1 at the point 5, 2. We can find the derivative at a point rather than finding the derivative function and then evaluating. Right? Don't use a hammer when that's not true. Don't use a sledgehammer when a hammer will do. Just use the hammer here. Let's just find the derivative at the point. F of 5 plus h equals the square root of 5 plus h minus 1. Right? Replace x with 5 plus h. Simplify. That's the square root of 4 plus h. We know that f of 5 is 2. I worked hard instead of smart here. Don't repeat my mistakes. 5 minus 1 is 4. Square root of 4 is 2. I should have already known that. The difference, f of 5 plus h minus f of 5, is the square root of 4 plus h minus 2. Once I have the difference, I make my quotient. Unfortunately, if we let h go to 0, I'm going to end up with 0 over 0, another indeterminate form. So, more algebra. I'm going to take this difference quotient, square root of 4 plus h minus 2 all over h, and I'm going to rationalize the numerator. So I multiply by the square root of 4 plus h plus 2 in both the numerator and denominator. That's a big jump with the equal sign, so let's see what's going on there. I'm going to make this a little bit smaller, move it up. Let's see what kind of work we have going on here. When I multiply my numerators, I'm going to get 4 plus h. I'll have 2 times the square root of 4 plus h and a minus 2 times the square root of 4 plus h, so they cancel. I'm going to have a minus 4. In the denominator, I'll have h times the square root of 4 plus h plus 2. Ugly, but there we go. The 4's cancel. My h over h yes, I'm going to be lazy right here. Tells me that my h's cancel, and that's how I get 1 in my numerator. If you need to, remember you're factoring out an h. I'll get 1 in my numerator over the square root of 4 plus h plus 2. This is not the slope of the tangent line yet. We haven't let the limit go to 0, and it's definitely not the equation of the tangent line yet. So the derivative at 5 is the limit as h approaches 0 of 1 over the square root of 4 plus h plus 2. When h goes to 0, this will be the square root of 4 plus 2. The square root of 4 is 4. Ha! No, it's not. The square root of 4 is 2. 2 plus 2 makes 4 in the denominator. The slope of the tangent line at this point is 1/4. The equation of the tangent line, therefore, is y minus 2 equals m, derivative is the slope of the tangent line, times x minus 5, right, given point, distribute the 1/4, add 2 to both sides, y equals 1/4 x plus 3/4. I know, at this point you're thinking, Tuesday, This video is way too long. I agree with you, but I couldn't find a good stopping point, so we're going to keep going. Pause it, come back to it later. You know, YouTube will save your spot. Find an equation of the tangent line. F of x equals 1 over x plus 1 at the point 0, comma 1. Well, I'm going to find the specific derivative. F of 0 plus h, that's 1 over 0 plus h plus 1. Nobody writes that 0 plus except for me. So that's 1 over h plus 1. I know that f of 0 is 1. So my difference, f of 0 plus h minus f of 0, is 1 over h plus 1 minus 1. But if I ever want to add or subtract with a rational expression, I'm going to have a common denominator. Nice that 1 can be written as h plus 1 over h plus 1. Here I'll have 1 minus 1, they cancel out. I'll have a negative h in my numerator, common denominator, h plus 1 stays. So now I find the derivative is, the limit as h approaches 0 of negative h over h plus 1 all over h. And when I divide by anything, let me just write this a little small here. Instead of dividing by h, I can multiply by 1 over h. Right? Dividing by h is the same as multiplying by 1 over h, and that's why my h's cancel. And I end up with negative 1 over h plus 1. The limit as h approaches 0. When h is 0, I'll end up with negative 1 over 1, which is negative 1. I love it when we have zeros involved. Y minus 1 equals the slope, negative 1, times x minus 0. Negative x plus 0. Add 1 to both sides to get the y by itself, and I'll have an equation y equals negative x plus 1 as the equation of my tangent line. Alright. Find an equation of a line that is tangent to f of x equals x cubed plus 2 and is parallel to a given line. Now this has three main parts. First, we have to know that parallel lines have equal slopes. So let's find the slope of the given line by solving for y. And the easiest thing to do would be to add y to both sides. Y equals 3x minus 4, so the given slope is 3. Our next step, we want to find all points on our graph that have a slope of a tangent line, aka derivative, that's equal to 3. So I'm going to find the general derivative. F of x plus h equals x plus h all cubed plus 2. And when you multiply that out, if you're familiar with Pascal's triangle, that'll help you. X cubed plus 3x squared h plus 3xh squared plus h cubed. Don't forget your plus 2. If you're not familiar with Pascal's triangle, you might want to look it up. It'll make life easier. Or just multiply x plus h times x plus h times x plus h, and you'll see that this is correct. Let's form the difference. F of x plus h minus f of x. Given our f of x plus h, when I subtract x cubed, that cancels. When I subtract 2, my 2 cancels. The only terms left are these 3 in the middle. Notice they all have an h. So when I divide by h, 3x squared h divided by h gives me a 3x squared. Here one of the h's will cancel. And in the last term, also one of the h's will cancel. I have my difference. Let's go on to the limit. The derivative, which is equal to the limit as h approaches 0 of 3x squared plus 3xh plus h squared. When h is 0, h squared goes away. When h is 0, 3x times 0 becomes a 0. I'm left with 3x squared. Fantastic. So I know my derivative function. I know I want my derivative to be 3 if it's parallel to the given line. So if f prime of x equals 3x squared, then f prime of x will equal 3 when 3x squared equals 3, which is when x equals plus or minus 1. Two tangent line equations we have to find. One through an x value of negative 1, and when I substitute, that gives me a y value of 1. And one through an x value of positive 1, and when I substitute, that'll give me a y value, of 3. Our third and last step is now to find the equation of both lines. Recall that the slope of each is 3 because it's parallel to the given line. So I substitute, find y equals 3x plus 4 for one equation and y equals 3x for the other equation of the tangent lines through the graph of the function parallel to 3x minus y minus 4 equals 0. An alternate definition of the derivative. The derivative of f at c. Remember how I said the difference quotient is a generalized slope formula? This is the slope. That's all it is. It's just a slope function. And the limit as x approaches c, that's where my delta x was approaching 0. That's it. The limit is what makes it work for nonlinear functions. So a probably not so quick example. If f of x equals x times x minus 1, when c equals 1, I want to find the derivative if it exists. So I'm going to take f of x, x times x minus 1, minus f of c, that's 1 times 1 minus 1, all over x minus c, so x minus 1. And this is the limit as x approaches 1. Notice that 1 minus 1 is 0, negative 1 times 0 is 0, so I'll end up with x over x minus 1, x times x minus 1 all over x minus 1. And this is the limit as x approaches 1 still. We're finding the derivative. The x minus 1's cancel out. That's the limit as x approaches 1 of x. And as x goes to 1, then x becomes, you guessed it, 1. So my derivative at 1 happens to be 1 for this particular function. But you know that's not going to be as easy as it is all the time. So let's take a look at 2 over x as my function and a c value of 5. I know that f prime of 5, the derivative using the alternative form, is the limit as x approaches 5 of the original function, 2 over x, minus f of c, so 2 over 5, all divided by x minus 5. First, we're going to simplify the difference in the numerator, and then we'll take care of the quotient. So, 2 over x minus 2/5. Let's get a common denominator of 5x. The first expression I'm going to multiply by 5 over 5. The second expression I'll multiply by x over x. This gives us 10 over 5x minus 2x over 5x. Once we have a common denominator, we can combine our numerators. 10 minus 2x over 5x is a fantastic numerator. But remember, this was just the difference. The quotient is divided by x minus 5. So 10 minus 2x over 5x, all divided by x minus 5, is the same as 10 minus 2x over 5x multiplied by the reciprocal times 1 over x minus 5. And at this step, I notice, hey, these seem kind of similar. How about if I factor out a negative 2 in my numerator? When I factor out a negative 2, I'm left with a positive x and a negative 5. But that x minus 5 cancels the x minus 5 that's in our existing denominator. X minus 5, x minus 5. I still have my negative 2 times 1, which is negative 2. I'll have my 5x in the denominators, 5x. Where are x? Well, the derivative at 5, using the alternative form, is the limit as x approaches 5 of 2 over x minus 2/5 all over x minus 5. What we just did on the previous slides is we simplified this difference quotient to get negative 2 over 5x. As x approaches 5, we replace x with 5. Negative 2 over 25 is our derivative at an x value of 5. I don't know about you, but I sure hope we find some easier ways of doing these derivatives soon. Once again, thank you to Desmos.com and their free online graphing utility for the graphs. They make everything so much easier to see.